Going live, going live. All right, in theory, we're live. Hey everyone, welcome to the third interview of this week. This week I'm joined by Professor Geraint Lewis, who we've been, I guess, friends on Twitter for a few years now. I've got a copy of your book, but I don't think we've ever actually had a chance to talk.
Not person to person. I think
No.
we've exchanged a few emails over the years, but first time is person to person.
Yeah, awesome. So for people who don't know who you are, who are you? What do you do?
Okay, so my name's Geraint Lewis. I'm a professor of astrophysics at the University of Sydney, and my research is focused on sort of the dark side of the universe. I'm very interested in dark matter and dark energy and sort of how we can measure it and characterize it and try and work out what it is. But I'm also interested in bigger questions. So I do some research in relativity, and I also do some of the bigger questions about the potential of our universe being just one of many universes in a multiverse and what that means, etc. So I try to stray into the philosophical side, but I tread very carefully.
Yeah. And I mean, you're kind of like a Swiss Army knife of all of the things that people have a million questions about regarding space and astronomy. So my hope is that people can, I've got a bunch of questions for you, but my hope is that people will also be able to deliver some tricky questions. And the sort of the trigger event that caught my eye and sort of caused me to reach out is just a couple of days ago, you posted a paper talking about the anthropic principle. Mm-hmm. And I really enjoyed it. And it's been making the rounds quite a bit in the, in the science skepticism sort of field. A lot of people have sometimes it sort of ventures into religious arguments and things like that. And of course, there's the classic Douglas Adams story of a puddle. So can you just explain what the anthropic principle is?
Well, so we should start by saying that the anthropic principle is not a single idea. And this is part of the issue. This is what leads to a lot of the arguments. It started, there's a number of key characters, but one of the main ones was Brandon Carter back in the 1970s. First called this thing the anthropic principle. And this is this notion that we have to be in a universe with laws of physics that allow us to exist. So, right. We live in a universe where we have a certain level of complexity given to us by the elements in the periodic table, the molecules that can form, and all that complexity eventually leads to us. And we can imagine hypothetical universes with different laws of physics where, gravity is stronger or electromagnetism is weaker. And it turns out that in those universes, it's very easy to wipe out that kind of complexity. So we have this question of the anthropic principle. We're in a universe that allows us to be here, which sounds like such a trivial statement. But when you look deeper, it's telling us something, I think something about the fundamental laws of physics that we have in the universe. And I'm very interested in trying to work out what that is.
Right. And so, I mean, when you sort of look at it from one perspective, you say, wow, the universe is perfectly tuned for life, for us to be here. That if the force of gravity wasn't what it was, if the atomic strength of the various, strong, weak nuclear force weren't exactly what they are to however many decimal places, then matter would fall apart, stars wouldn't form, there wouldn't be life, and there wouldn't be us. And so it really feels like the universe is fine-tuned for us. But then if the universe didn't have these characteristics, then nobody would be here to say, wow, isn't this universe perfect? Or I guess barely habitable is the universe that we've got, right?
That's right. Exactly. So some people treat the anthropic principle as a trivial statement, right? I mean, we couldn't be here to ask the questions if the universe wasn't the way it is set up to be. So the question is why does our universe have these properties? And of course, what we mean by the properties are the laws of physics and the numbers that go into the laws of physics, the strengths of the forces, the masses of the particles, etc. Why those numbers? Now, there's a couple of possibilities. Number one is that that's it. This is just the way that the universe can be. But that's a very unsatisfactory answer, right? Because it doesn't really answer anything. You've basically shrugged and said, I can't do anything with this.
Right.
As you mentioned, other people turn to the religious side, and they say that there was a being that made the universe this way, and we are some sort of central being in that universe because of this God creature, whatever overarching sort of idea.
Yeah.
I wonder then, is there a scientific explanation, right? Is there a scientific explanation for why our universe is the way it is? And, there have been proposals, and I said the side I sort of lean towards is this notion that our universe is not alone, that our universe is one of many universes in something called the multiverse. And each of these universes gets dealt a hand, which is their laws of physics. Most of those universes are dead and sterile, but we ended up in one which has the complexity which hosts us.
Right.
Right. So that's the kind of like overarching picture, but there's no actual answer at the moment. This is the thing that drives me crazy, is that people sort of slap down and say, right, that this is the answer to why it appears fine-tuned. We don't know why it's fine-tuned or appears to be fine-tuned. I just think it's telling us something deep about the universe.
But I mean, if you sort of think of it from like however many independent constants that there are in the universe, the alpha constant and the force of gravity and so on the one hand, there could be some random number seed that actually underlies all of them. It's just a matter of the theorists and the experimenters getting to the bottom of how they're actually all connected. And if you find the one number, it actually generates all of those other factors beautifully, because that's, the one theory to rule them all. But that still, I guess, maybe that random seed is being regenerated with each new universe. And so you're still getting the same problem, even if you do connect all of those forces. Yeah. But it doesn't necessarily imply that all those different universes are that they can even exist. Like, it's just, we've got one shot, there's a universe, here it is. And it's the only way that it could have been, right?
So there is an idea that physics can fix it, right? That eventually, if we think really hard, there will be no freedom in our physical theories. All of the physical constants will be related to pi and e, or just, be able to write them down. We'll know exactly why the electron weighs what the electron weighs. But all you've done is move the problem somewhere else, right? Why that theory, not another theory where the numbers would be related differently? And so, I just feel like at the end of the day, the physics will fix it. It just ends up being unsatisfactory, right? You just end up having to, at some point, to shrug your shoulders and just go, well, that's the way it is. And, some people can sleep at night, but for me, that just, it bothers me.
Well, but doesn't, I guess, finding out that, if there is, in fact, a multiverse, then that still just pushes the problem one step back. But maybe that's just someone else's problem at that point. Like, that you're still having to then sort of sort out what is the cause of all of those.
That's right. And, look, if that's the quest of science at some level, isn't it? I mean, we are really just kids going, why? And problems do get pushed. And clearly, if we understand how our universe came into being and there being a multiverse, there will be more questions. And that's good, because that keeps me employed. It will at least open the door, right? We will understand the universe better if we can answer some of these questions.
So your job as a scientist, as a cosmologist, is to try to come up with some kind of experiment, some way to tease out in an experimental fashion what might be underlying some of the properties that we see. Have there been any productive ideas to go down that route?
There have been suggestions. Of course, what we lack at the moment is we really lack an understanding of how our universe came into being, right? We've got this problem with relativity on one side that gives us the expansion of the universe, all that large scale stuff. Quantum mechanics on the small scale. They don't play well together when they both have to fight for domination. And in the early universe, they were both important. So there's a window, a door, I should say, that's closed to us about the actual start of the universe. So we don't know what came before. We don't know if there was a before, etc. But people have speculated about possible signatures we could see in our universe if we were in things like a multiverse. So this has been proposed and come and gone several times. There's been these ideas that if our universe is like one universe floating in a high dimensional space and we've collided with another universe, then there could be a pattern written in something like the cosmic microwave background. And people have searched for those kind of patterns. And like lots of things, when you stare at them and squint enough, some people see patterns, some people don't. So people are trying, but we just don't have the robust predictions yet to test these ideas. And my hope is that we will do. But, we're looking for peculiarities in what we see, cosmic microwave background, makeup of the universe. Right. But I think it's going to still be a little while until we can open that door to the birth of the universe before we can say what a concrete prediction of us in a multiverse would be.
I mean, there are a couple of fairly big experiments in the works. There's the European Space Agency's LISA, which is going to be searching for gravitational waves with an expansion up to the Big Bang Observer with, 12 satellites or some extreme number. It may very well be able to detect the primordial gravitational waves left behind from the Big Bang. And then there's also, for example, extreme upgrades to some of the neutrino detectors that might be able to let you detect primordial neutrinos. Do any of those, do you think, deliver the goods, or will they?
Well, yes and no, right? So the primordial black holes and the primordial neutrinos, they are something that happened essentially in the early stages of the universe, but still a long time after the birth in terms, if you look at the evolution of the universe. But like all experiments, they've got the potential to show something doesn't quite fit. So if we get the gravitational wave spectrum of the primordial gravitational waves, and it is different to what we predict from inflation, then we have to ask ourselves, well, why is there a pattern written into these gravitational waves that we don't expect? And hopefully that will push further back. The neutrinos, I think the neutrinos came on the scene too late, right? The neutrinos, at least in the standard model, appears essentially after inflation and into the early stages of the universe. But again, if there's something weird about the properties of neutrinos, we have to ask, well, is there something left over from an earlier epoch? So, we're chiseling away, always looking for those things that don't fit to tell us which direction to look in.
And then, of course, there's us attempting to actually simulate the conditions of the Big Bang in some kind of enormous experiment here on Earth.
Yes. Yeah. Oh, yes. So, I mean, there's physical experiments, of course. There's smashing stuff together at CERN to try and recreate the very high energies that were in the early universe. There's also the theoretical side, which is it doesn't get reported as much because pictures of the Large Hadron Collider are always cool compared to a picture of a whiteboard with some squiggles. But those calculations that people are pushing, right? The ideas of calculating quantum mechanical aspects of the very early universe. Again, eventually we will see those written into the cosmic microwave background, and we're going to look for where things don't fit to tell us what we need to do to basically build those ideas that we're still hunting for this theory of everything. And that's going to be, I think, one of the big steps for us in understanding the universe.
But I know that the Anthropic Principle sort of splits into two versions, the greater and the lesser. The greater being sort of, I guess, observers are required for the universe to exist at all. And the lesser is like the universe, if there wasn't anybody to observe the universe, well, that's just a shame. Right.
Yes. So there's confusion because firstly, there was Brandon Carter, who had his strong and weak anthropic principles. And they were more about the conditions of the universe than anything else. But then in 1986, a book came out called The Cosmological Anthropic Principle by Barrow and Tipler. And it's a very influential book. Mm-hmm. And they sort of redefined the anthropic principle. So it's not just that there's a split, but there are now different versions. And they had this stronger idea that the universe, if a universe has the conditions for observers, then observers necessarily come into being. And that's where the arguments really start to fly in, the meaning of the anthropic principle. And I think there's a lot of scientists wouldn't go with that stronger kind of picture that life and intelligence must arise in the universe with with complexity in it. And they went even further, of course. They have this thing called the final anthropic principle.
I haven't even heard of that. Okay.
Oh, have you ever?
No.
Oh, so this is the idea that essentially we will all be reborn again in the future in giant computers, right? So they've taken the anthropic principle down a certain path, which has led to lots of people saying, "Oh, I want nothing to do with that." Whereas the statement about the conditions in the universe needed for life and intelligence to arise, which is the weaker statement, I actually think is an important statement, especially if we do get competing theories for how universes arise, right? You better hope that your theory at least can predict one universe like this one, right? In which we inhabit.
At least.
Because if your theory, at least one. Because if your theory doesn't, then it's dead in the water. So it is important at that level. But I said the landscape of the anthropic principle is quite murky because of these different definitions.
But when you look at the universe that we live in, I made a brief mention about this earlier on, that the universe itself is just barely habitable. When you think about a universe that could be well-tuned for life, well-tuned for humanity, I can imagine an infinite number of universes that are better than this one. This one is just this side of completely lethal.
That is true. So, but as you said, you can imagine. So, what kind of universes can you imagine that would be more habitable? How would you make a universe that's more habitable?
I say one that was a nice temperature and had nice breathable air for the entire universe.
So okay. So what you want to do there, right? Is you want to fill the universe with air with this.
Sure. I can see where this is going. Yeah.
Yeah, but what you've done then is you've put so much mass into the universe that it automatically collapses.
Right.
So it's kind of weird. We actually need a large empty universe for several reasons. Number one is that it doesn't recollapse. But you also need a cold background to the universe so you can have flows of energy from the sun to the earth into space through the things that powers life. Now, you could make the universe more habitable by, getting rid of all those boring M-type stars and having more G stars, etc.
Yep.
So you could do that, and you increase habitability a bit, but you can't make the universe packed with life because such a universe, I said, would automatically collapse.
Right. We could double it, say. With some creative accounting, I think we could double the amount of life, the habitability of the universe, maybe. Less gas giants, more terrestrial planets.
But you remember, like, I'm a cosmologist, a factor of 2 is irrelevant.
Of course.
I don't get out of bed for less than a factor of 10. So,
Right.
that's the kind of thing is a factor of 2 isn't really more habitable, right? It's still mostly empty, dead space, right? So it's... Again, I agree that you could make it more habitable, but just how habitable you would want it, I think, is a different question.
Right. So not enough to make a cosmologist pay attention.
Yeah.
Right.
Absolutely.
Yeah. All right. Well, I think it's a fascinating idea, and I think it's it is easily dismissed, and yet I think it's a wonderful example where philosophy and science can sort of rub shoulders with one another and inform each other. And I think it was great. I really enjoyed the paper, and I sort of enjoy thinking about it. I've ruminated on it a few times. Now I want to talk about your book, and this book, and so I got this last year, I guess, and we didn't get a chance to talk about it, but I think it's great. And the gist of the book is, if you think you can overturn the modern theories of cosmology, if you think you've got a better idea for the Big Bang, dark matter, dark energy, all of that kind of stuff, relativity, Einstein was wrong, then this is your guidebook on how to get attention from the astronomers and cosmologists and to get them to agree with you, and then it's Nobel Prizes all around. What was what triggered this book?
So I wrote the book with my colleague Luke Barnes, and we give a lot of public talks on cosmology. And at the end of those talks, there's always really good questions, and kids ask the best questions. But in the audience somewhere, there's usually somebody, and I wouldn't fully stereotype them, but they tend to be an older male, they tend to be a retired engineer, and they tend not to like the story of modern cosmology. There are aspects of the universe as we've described it to them that they just don't like.
Yeah.
And they have better ideas, right? It's what if it's electromagnetism and not gravity, etc. So we got so tired of answering the same questions, because we get these by email as well as that, and it's still paper mail.
Oh yeah. I get so many. Like, it's just like I get so many of these all the time, and I'm not, I'm just a journalist. I am not the one who is in any way qualified to answer these questions.
Yeah. So we do try and answer them, but what we find is that most of the people that are proposing these ideas have no idea really what, firstly, modern science is and what the scientific process is, or even really what modern cosmology is. And in the sense that, why do cosmologists believe, in quotes, what they believe? And so what we wanted to do in the book is we wanted to lay out a couple of things. Firstly, the scientific process, how we go about asking and answering questions, but then also getting that message to other scientists. And so, there's this issue about, writing a scientific paper that goes into the literature, gets peer reviewed, etc. Speaking at scientific conferences, being prepared to, have your ideas attacked and dismembered because, somebody's found a flaw here, etc. So the scientific process is something that these people are not engaged with. And they also don't understand the scientific evidence that has brought us to where we are and the state of play. So we get lots of things, questioning things like the redshift, right? Mm-hmm. Astronomers talk about the redshift and how do you know it's this and not that, etc. And they don't realize that cosmology has moved on, right? The thing that keeps cosmologists up at night is not the nature of the redshift, because that is an experiment that's been done thousands and thousands and thousands of times, and we've moved on to something else. So what we want to do is lay out the sort of key observational evidence, and then also show where some of the alternative ideas that have been proposed for the years, how this evidence brought them down. So, that theories, stand or fall based upon how well they can describe the universe, and many, many of them get consigned to the scientific rubbish bin.
Mm-hmm, mm-hmm. And in general, scientists are grateful when you've helped them shuffle their theory off into the garbage, because it means one less bad idea that now they can spend their time working on the good ideas that remain, as opposed to, ideally, in the perfect world.
Yes, in general.
On. Yeah.
Yeah. So, except, scientists are people, and scientists have egos and personalities. And I think it was Max Planck that said that, science progresses one funeral at a time. And, you have greats of science who do great things, but they have their pet idea and they take them to the grave. And, one of my scientific heroes, I don't have that many heroes, but one of my scientific heroes was Fred Hoyle, who, made great contributions to science in terms of how stars work and even how the early universe worked with the formation of elements. But he had this viewpoint of the steady state universe, which he proposed in the 1940s. He died in 2001, and he was still trying to push that idea. And even though the evidence time and time again said this idea doesn't work, he held on to it. So in an ideal world, scientists would say, yes, that theory is done, I'll put it in the bin, but some like to hold on to them.
Right, yes. But I know there's lots of really great heartwarming examples of scientists learning convincing evidence that overturns their theory, and they're yes. grateful. And that just every time you're just like, yes, that's how science is supposed to work. Yes. But you get these theories from people. What is if a person sees, just doesn't like the word dark matter, doesn't think that the universe is, all that stuff is real, doesn't thinks that Einstein is wrong, just in general, what is the best way for them to try to make some progress and maybe see if they're right or wrong? And if they are right, then get the accolades for it.
Well, what they need to do is to understand, let me be careful with my words here. often these ideas are ideas in terms of words, right? They're ideas in terms of a story. What if the universe was? And of course, to a physicist, that's only the starting point of a scientific idea, right? That idea has to be turned into the language of physics, which is mathematics. And from that language, you make a prediction, and that prediction is what you hold up to the universe. And what we find is that normally people don't get past that what if, right? What if Einstein is wrong? Well, so what is your alternative? What is your mathematics? I can go out and test this. Oh, I don't have the mathematics.
Yeah, well, let's work together on it. We'll share the Nobel Prize. Yeah,
that's right. We get an awful lot of that, actually. If you could just help me with the maths, and they don't realize, to them, the maths is the add-on, but to us, the maths is the theory. That's the thing that we test. So it's very important to understand what physics is and what the scientific process is and how you make a prediction. Right? It's hard to make a prediction out of a story. You make a prediction in physics out of equations. So for many of them, it really is going back to the drawing board. But you realize that they say Einstein is wrong, and they don't like Einstein because they've read some popular science book about something about going up and down in lifts and something about reference frames, but they've never read the mathematical aspects. And the reason why physicists love relativity is it's the mathematics. It's incredibly powerful in terms of the mathematics. They don't care about that story side of stuff, but the mathematics you can do so much with. And so understanding the scientific process, I think, is an important one that they tend to miss, which is why we wrote a big chunk of that in the book. And we still get people sending us ideas and asking us to help them turn them into papers. But yeah.
But now you can say, just buy my book, and then that should keep them busy for a couple of years.
That's what we're trying to do.
Yeah.
And of course it helps pay off the mortgage, but yeah, that's the advice, is that we wrote this for people semi tongue in cheek, right? Because we also are trying to sell the story of why modern cosmology is a success. But it really is the recipe for what you need to do if you do have a new idea. So I think if people followed it and can explain the evidence and can explain one more observational fact, then they have done better than the standard cosmological model.
And so, near the end of the book, you turn the tables a bit and you say, if you want to help, here are the problems that do keep us up at night. These are the challenges that we still don't understand and have answers that we're satisfied with. So what are some of the big questions that still, if anybody could show up with a useful theory and the math, they would be celebrated by astronomers?
Well, there's several of them, right? There's the really big questions that we really want to answer, and that's a question of, like, where did the universe come from and what's going on in the center of black holes. But if you talk to cosmologists who are looking at the cosmological model, right? What is the nature of dark matter? What is the nature of dark energy? They are two key questions, but we don't really know fully how to answer those yet, and people work on those. But in terms of observations, the things that bother us are now to do with the small scale universe, right? So the attention is now focused on objects the size of galaxies, right? Because we think we understand galaxy formation, that gas pools together and forms stars, etc. And that all sort of works, except there are weird features in the universe when we observe it. In terms of, we expect a galaxy like our own Milky Way to be surrounded by dwarf galaxies, smaller galaxies with maybe 1 billion stars each. And they should be orbiting kind of randomly. But what we are seeing in the Milky Way and in Andromeda is that there are these well-defined orbits, sort of planes of orbits of dwarf galaxies, which are not in standard cosmological model.
Right.
Now, we don't know, is that something that we've missed in terms of the physics of gas? Because gas physics is hard. And you add magnetic fields and things get even harder.
Yeah.
Is it something?
What's the term for that? I forget. It's like, magnetoplasma. I forget what it is.
There's magnetohydrodynamics.
There you go. Yeah.
So the physics of gas is difficult. The physics of dark matter is easy, right? The gas can shock and collapse and form stars. Have we missed something in our physics of gas that we need to add? Or is there something weird about the universe on this small scale that is creating these structures? And there are those that have proposed that it's not anything to do with gas, that it might actually be our understanding of the laws of gravity that have problems on these scales. So people are looking at the small scale universe, trying to understand the detailed structure. And I said, we don't know if it's something within our laws of physics, i.e. gas, or if it's telling us that physics on small scales, on the scales of galaxies, need to be looked at. But these mysteries, there's a bunch of them which really have been around for a while, and people are scratching their heads. I think we mentioned this one in the book. There's lithium. Lithium is one of these annoying elements in that one of the great successes of cosmology is the primordial elements formed in the Big Bang. So hydrogen and helium and a little bit of lithium. And the hydrogen and helium, that works perfectly. But lithium is out by a significant amount from our predictions. And we don't know, again, is that telling us something about the early universe we don't understand? Or the way that lithium has been processed in stars in the universe, right? So, lots of these problems, they are like, oh, it could be important, or we could have missed something sort of obvious. So we don't know. We don't know. And I guess physics at the frontier is always like that, right? You really need to be sure you've really ruled out the boring stuff before you can say, oh, look, this is something new that I've learned.
And so I think the lithium is a great example where it could be that, as you say, we just don't understand how lithium is processed in stars later on in the universe, or it could very well be that this fundamental piece of evidence for the Big Bang, the amount of hydrogen, amount of helium, and amount of lithium left over, are not the numbers that you would expect, and therefore the underlying theory itself has some serious flaws that need to be rectified. That's got to be kind of frustrating because you don't know whether this is something that, oh, here it is. There was one mystery that is feeling like it's fun to watch it get solved. And, I've been reporting now for over 20 years, and we got to watch like the missing mass in the universe, not the dark matter, not the dark energy, but the missing regular mass get chipped away bit by bit by bit. And now it really seems like it's all been found. Mm-hmm. Go ahead.
Oh, yeah. So no, that's precisely it, right? But as you say, that's several decades worth of various scientists working in various regimes to say, all right, we've now accounted for the baryonic mass, the normal matter in the universe. I think often that kind of multi-decade approach to answering a question, that sort of gets lost in the reporting of science now and again, and that there's the sheer number of people involved. But it is kind of satisfying when you go, oh, good, we've accounted for all that mass. Right. But then you realize so we know how many normal atoms there are in the universe. If there is a problem with lithium, doesn't appear to be the normal atoms which are the problem. So there was something else in the early universe that we have to focus on. And again, it's where do we start? What are the possibilities that we can play around with? So unanswered questions.
One of the ones that you mentioned, and I even see the conversation happening in the chat, is that people don't like dark matter. And I guess I used to sort of understand because it's just like it was, but they, often there's even a lot of like almost insults to scientists for coming up with some stupid term because they make up something that they don't understand. And yet when you look at something like, say, the neutrino, which is like almost precisely behaves almost exactly the same as dark matter, nobody has a problem with it. They're like, of course there's trillions of nearly invisible particles passing through my body right now, and they don't interact, and I can't see them, and they're there, and they're coming from the sun, and that's all just fine. But dark matter, no way. Is it the name?
Well, I think the name itself doesn't really help. So you have to be careful, right? So as a scientist, when I talk about dark matter, right, I talk about matter, blah, 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 and I talk about dark matter in the universe. What do I mean when I say dark matter? What I mean at some level is that there are observations that I have made with a telescope, and the observations do not work if I take into account only the matter that I can see. So if I look at the speed that galaxies are rotating, I've done those measurements. I look in gravitational lens systems. I can calculate how much mass is there, and there's always apparently more mass than there is just invisible matter. But in reality, what I'm saying when I say dark matter is that at some level it's a parameterization of my ignorance. There's something not quite right that, in terms of just the visible matter. So it could be that there is actual material out there which doesn't interact with light and is a physical substance. And that's what people are hunting for in various experiments. But I know in my mind as well that there's a possibility that gravity doesn't work, right? We've got gravity wrong in these scales.
Right.
But science is a betting game, right? The question is, how much are you willing to bet that it's alternative A versus alternative B? Alternative A, that it's material, well, that's actually quite reasonable, right? Because we already know that the universe is made up of particles, etc. We know that the standard model of particle physics is not complete. It can't be complete because there's no gravity in there. And we expect that when we add to the mathematics, there will be more particles. And it seems to me quite reasonable that one of these might be the dark matter particle. But, I always keep a few bucks on the gravity might be wrong one, because that's an interesting flutter, because that would open up new directions in physics altogether. So it's a bit of a juggling match.
Or dark matter is black holes. Like that one won't seem to go away.
Well, except what we're doing is we're closing the window on just how much mass there can be in black holes, right? We know that they can't be black holes with the mass of the sun, because we would have seen those in gravitational microlensing experiments, and actually down to about the 10th the mass of the sun. So they have to be weird kind of black holes. They have to be sort of planet-sized black holes. But the window of possible black hole masses is closing from both sides. So it could be, but it also, as I said, I think very soon the black hole option might be ruled out completely.
Right. And so, if you can't make a direct observation of what it is that you're looking for, then you can at least rule out every possible thing you can think of.
Yes.
But that still doesn't give you the answer. It just tells you what it isn't.
Exactly. But a lot of science is that, right? You rule out possibilities. You keep ruling out possibilities. When would people be satisfied? When would somebody be satisfied? Do I have to have a dark matter particle in a box and say, this is it,
right,
for people to be satisfied? Or does it have to be produced at CERN? Or, what level do people want as an answer to this question?
That's an interesting idea. I've never really sort of thought of it that way, that it's just like, are you happy when you know what particle releases dark matter particles? Are you happy when you know when those dark matter particles formed? If you can get to the point that you know it's not black holes, you know that it's there, you know it's not a misunderstanding of gravity, it's definitely a particle, it's definitely slow, it's cold, it's slow moving, it has this kind of a mass, it interacts very weakly in this way. Like, what more do you want?
Exactly.
Yeah.
So I guess there'll be something from particle physics experiments eventually, but the particle physics experiments are going to be like the detection of the neutrino, right? We're going to say, oh, there's something missing, right? Because you're not going to be able to capture the dark matter particle. You'll see that there's a gap in terms of the expected amount of energy. And again, like the neutrino, you'll say, oh, I guess then there must be a particle produced there, and it has the properties that match dark matter. Are you happy then?
So are you? Yeah, exactly. Are you not amused? All right. Well, I wanted to get people. So people, if you're in the chat, and I know Arjun and Six Bob Bowman, there's a bunch of people here who've got some questions, like your toughest, your hardest, your most lethal space, astronomy, cosmology, dark matter, dark energy questions. Please hit us with them. This is your chance. We've got a true pro here. Yeah. Arjun asks, could we determine that we know gravity by our study of gravitational waves, like at different length scales?
Sort of. So the issue with gravity as we as we understand it's now written into Einstein's, it's written in the language of Einstein's general theory of relativity, right? Which is to do with fluctuations in space-time, they travel across the universe, etc. In terms of if we want to modify gravity, you can either modify it by having some completely different theory, and we just know that at the moment, none of those theories are really proper relativistic theories, so they don't really have gravitational waves in them. So we can't talk about the signature of what we expect for gravitational waves from theory X, because they haven't really been matched with Einstein's theory. But what people are doing, of course, is that when they look at gravitational wave signatures, they are looking for deviations from what you expect from relativity. So people are looking precisely at sort of like the signature you get when two black holes merge and the ring down, and they're just looking for any deviation that might say general relativity is not the complete story, right, and we need to add something. At the moment, though, the universe is refusing to play ball, and every gravitational wave signature looks just like we would predict them to be. So people are still searching.
Right. I mean, I know even like, you know, we talk about this idea of the crisis in cosmology, that there's these two ever tightening measurements of the expansion rate of the universe, and their error bars don't overlap. And cosmologists are giddy about this. They're so happy that there's something complicated that is going to help point the way in the directions of new ideas in the large scale structure of the universe.
Absolutely. This is something that we try and get across all the time, right? You don't get a Nobel Prize for saying, oh, I just agree with everybody else. You get a Nobel Prize for saying, this is different and this is a new direction that we go in. And we've seen it in the G-2 results for the new one this week, right? So the particle physicists are also looking for these experiments where things don't work because it has the potential to open new doors. So, but again, we are still faced with that possibility of the two measurements of the Hubble expansion. Is that to do with errors in the experiment, or is it something fundamental about the universe? And as you said, things are definitely separated at the moment, but there are lots of different steps in there, and people are going through with a fine-tooth comb now just to check all the calibrations are correct and are carried through. So yeah, it's exciting, but it's not super exciting yet, right? So it might get more exciting, or it might just go away. So,
right,
you know, fingers crossed.
Back to what we talked about earlier. It might just be that it's not important. It might just be that there is a true, legitimate, complete misunderstanding of the way the universe works. You know, could be one or the other. Let's find out. The Delicious Plum asks, does a dark matter particle cast a shadow?
Cast a shadow? Mm-hmm. It depends what you mean by cast a shadow here, right? So a dark matter particle doesn't interact with light in the same way as our material atoms do, right? Because our atoms carry charge, and that means they can interact with light as it travels through. But dark matter does interact with light gravitationally. So we do see the paths of light rays get distorted by lumps of dark matter in the universe. And I actually did my PhD on gravitational microlensing, which is studying this entire topic. So you don't get a shadow as such, but you do get optical illusions because of dark matter. So you can see multiple images of the same distant object, and where that object would have been without the dark matter is no longer there, right? And that patch is now dark. So we get optical illusions, and we do get brightness and darkness where we wouldn't expect them due to the presence of dark matter. And in fact, this is one of the powerful methods of measuring just how much dark matter is out there. So it can do some cool things.
Six Bob Ohms asks, do you think a research AI will solve the final theory of everything, or will it be a human?
Oh, I have conversations with my wife about this because she works in synthetic intelligence. And what we don't know yet is whether or not AI can come up with new ideas, right? AI can do lots of interesting things. It can find correlations between various kinds of measurements. But can it come up with a new idea in the same way that, de Broglie famously asked, can an electron behave like a wave? And from that, we end up with all of modern quantum mechanics. We do not know if AI can have that creativity because we don't know how it works in our head. So how you program an AI to do it, we don't know.
Yeah.
I've read various books which say that AI will spontaneously one day come up with creativity, but exactly how it does that, we don't know. And I've read others by even Roger Penrose, I think, had an article recently that AI will never be anything other than a clever calculator, right? It can do great calculations, but it will not be creative. So it can mimic great art, but it will never come up with great art.
Right. I think about this a lot as well. And I think that where we're going to see a lot of really productive work with artificial intelligence in the medium term is this idea of, they call them centaurs. I don't know if you heard about this, but like you take chess masters and you pair them up with a computer. And so the computer is doing the heavy sort of looking forward on the chess moves, and while the human is sort of coming up with larger strategy ideas. And it's between those two people together or the person and the computer, that you get the strongest chess players that can possibly exist. Better than any human, better than any computer. It's the two together. And there's some really interesting ideas in using artificial intelligence, as you say, to make these really interesting correlations that someone in the field of biology might have just noticed a pattern that is actually very appropriate to what you're doing in cosmology. And you would never even think to go and take a look and have a conversation with them. And yet let a computer grind through all papers ever done, looking for these connections and sort of being a matchmaker and going, hey, you should talk to this person over here because you're kind of thinking of the same thing, even though you don't even realize it. And I think we'll get a huge boost in productivity in the short term.
That's right, but you still have the human mind in there at some point, right? Because, as I said, the notion of coming up with something new, finding correlations is one thing.
Yeah.
Coming up with an explanation, that's another thing.
Yeah, I disagree with Penrose, but I mean, that's sort of a dangerous thing to do because he's a very smart guy. But I do think that eventually our artificial intelligence, like I don't feel like there's any limit to, like, the human brain is just a meat computer, and so if you can make a computer do the same as the human brain, then why wouldn't you necessarily be able to start getting some of that emergent behavior that is capable? It's just going to be difficult and probably take us a while.
And actually, one of the things that bothers me is that even if we do end up with creative AI, are we going to be able to understand it?
Yeah.
Right? I mean, it might. There's this prediction, like AI, if it becomes intelligent, etc. The day that it is as smart as the dumbest person on the planet, by the end of that day, it'll be 100 times smarter than the smartest person on the planet. And so we might not understand the answers to the questions that it's put in front of us because, we're semi-evolved monkeys that were walking around the savannah a few 100,000 years ago. So, that's something we might have to be prepared for.
Yeah, that we'll have like one afternoon where we can get along with our, have interesting conversations with our future robot overlords, and then
absolutely,
and then boom, they're just off turning the planet into computronium. But that's got to be interesting. I mean, it's a great overlap with your partnership with you and your wife, that you can have these kinds of conversations, which I think is great.
We do talk about other boring stuff as well, like,
Sure.
like the mortgage and bills and things. But other than that,
yeah. Grumpy asks a similar question. We can collect so much data now and trust it to programming in models and supercomputers. Are we missing what a human would see? So is there an over-reliance on computers and computing at this point?
Over-reliance? I wouldn't say there's an over-reliance. The data taken has become incredible. I'm not sure if your listeners know that many experiments, like the Large Hadron Collider and the Square Kilometre Array, right? They have supercomputers at the experiment, and they throw out much of the data as it's taken because the data volumes are so huge that you can only record a subset of the data. But what has also happened, of course, is that the tools that we have developed for working with that data have also increased at an incredibly rapid rate. So this entire field of machine learning, and it's now a massive part of modern science. And I have students working in one published a paper recently on using machine learning techniques to hunt for dark matter in the center of the galaxy. And it's a very powerful way of approaching these problems. It's something that you could never, ever do with paper and pen, right? So I wouldn't say there's an over-reliance. I say that it's a key aspect of science. And one of the things that I try and encourage all students to do is to learn that side of science as they're becoming researchers, etc. Are there things that we're missing? Possibly that there are things that we're missing, but there's definitely more things we're picking up because we can just work with immense data volumes that we didn't before.
Yeah. Hal McKinney asks, why are neutrinos not considered a candidate for dark matter? Why have you ruled them out?
Oh, because we've been able to measure their mass. So originally, it was thought that neutrinos were massless. That's when we first wrote out the standard model and we had them in there. But there was experiments that were done in the 1990s where people showed that neutrinos can change their type. They flip from one neutrino to another neutrino and back, etc. This is neutrino mixing. And this gives you a measurement of how much mass they have. And what we can show is that they're just not massive enough to be dark matter. So they're numerous, but yeah, they're just not heavy enough to be a dark matter candidate.
Now, is that because there just aren't enough sources that could have produced them, or from the Big Bang and from stars, or is it that just there's I don't know, not enough of them? How does it work?
So we know the expected primordial density of neutrinos, because that's related to the primordial density of photons, which we can measure in the cosmic microwave background. So we know sort of in my hands, I know how many primordial neutrinos are in here. And so if you just multiply by the mass, that just tells you that how much mass in the universe is due to neutrinos, and it's just not enough. They would have to be considerably more massive to be a dark matter candidate.
But I know also, cosmologists say that they're looking for cold dark matter to explain it as opposed to hot dark matter. So isn't it also sort of part of the speed of the neutrino moving close to the speed of light compared to dark matter seems to be moving slowly?
Yes, I'm going to clarify one thing in a second, but you're right. So neutrinos also move very quickly, and that means that they stream large distances very effectively, which means that they don't clump very easily. And so that's why we think dark matter is cold dark matter, in that it has slow velocities, which means it can clump together into galaxies. Now, some people have proposed a cousin to the neutrinos that we know. So we know there's 3 kinds of neutrinos in the universe, but people have proposed a heavy neutrino called a sterile neutrino, which is not really part of the standard model, but it has similar properties to the standard neutrinos, but is more massive. So it behaves more like dark matter. So it's a candidate, but exactly where that candidate fits into the standard model, we don't really know. But we're awash with candidates for dark matter. So we have lots of different potential particles.
Right. We had someone talking, we were talking to earlier or last week that the axion is another potential particle and so on. And I guess it's just whatever people have focused on. All right, I got one last question for you. David Hagmark asks, if a friendly donor were to hand you, say, $10 billion earmarked for experiments in your field, how would you spend it? And then he also says, no, sorry, I'm not that friendly donor. But what bang for the buck, what do you think would make a really productive step forward in our understanding of the cosmos? To answer the questions that you want answered.
See, I've never had $10 billion. This is not something that I've given a huge amount of thought to.
Yeah. You write for a grant and they give you 250,000 Australian dollars and you're grateful. But yeah, I know.
Yeah, exactly. Yeah. So there's a couple of things. Firstly, if I'm just allowed to bank the 10 billion for a little bit, what I would do as a starting point is that I would invest in education in terms of science around the world. In that, I think people don't realize exactly how small the number of people wondering about the universe, wondering about particle physics really is. And we have immense number of minds around the world that don't have access to scientific education. And I think that would have a really big bang in terms of the theoretical push on where we should be working, right? So, there's investment in universities in all kinds of countries, including Australia. I would say that we need more science graduates. From there, I think that would give us the idea of what do we need to build? Do we need a sensitive gravitational wave detector? Do we need a bigger telescope on the moon? Do we need a more powerful particle accelerator? Or do we need a different kind of experiment altogether? So I wouldn't want to put 10 billion in one basket right now, because I don't think we know what the next level of experiment should be. But I think with enough investment in people, that we could know what it would be in a decade or a couple of decades' time.
I mean, you probably know as well as anybody how few jobs there are in that field, that there are, in some cases, hundreds of people coming out of a university who are applying for a single research position. So I don't know whether more people going through the educational side of things would help in the output side of things. Like we would really need a more fundamental appreciation of the people doing the work by governments and so on before I think that you could really match that up. I would feel sort of heartbroken if you had 1,000 people trying to fight for one job.
That's right. But when I say invest, it's not only at the educational level of having undergrads, but in your own country of Canada, right? You have the Perimeter Institute. Mm-hmm. So you can build an institute and, build it and they will come. And around the world, there are the Kavli Institutes. And these institutes, which have hundreds of people in them, they make a difference. They make a real difference to the push of science. And we don't have them in Australia, right? We don't have any Kavli Institutes or Perimeter Institutes. But I think as well as investing in people at the raw education, you found those kind of institutes. Yeah. And 10 billion would buy you a lot of institutes, right? Because essentially you need a building and you need salaries and off you go.
So you'd spend your money on people.
Yeah.
That's a good
I'm an
answer.
Optimist.
Yeah. No, I can't argue. Geraint, the book is the Cosmic Revolutionaries Handbook. It's been an absolute pleasure. If people want to follow you more, where should they go?
So I'm on Twitter at cosmic_horizons, and I enjoy answering questions on Twitter, so people should feel free to post things there. I also have my own website where I run a blog on there where I just dump random bits and pieces. So that's geraintlewis.com. People can feel free to contact me there, submit a question. I'd be happy to answer it as well.
Wonderful. Well, thank you so much for taking the time to chat and answer my questions as well as the audience's questions. And if you do figure out what dark matter is, would you let us know?
You'll be the first to know.
Perfect. Thank you so much.
Okay.
All right. Take care.
Thank you. Bye.